So, good morning everyone. Thanks for being here. Apparently, well, it's a small audience, so I think it's totally okay if everyone interrupts me whenever you have questions or comments. So we're in a very relaxed setting. So I'm going to talk a little bit about planning with state-dependent action costs today. These 90 minutes will be roughly split into 60 minutes, where I will talk about theoretical stuff, and then in the last 30 minutes or so, Florian will talk about more applied or practical considerations. But let's start with the theoretical part and some background. First of all, what are state-dependent action costs? For that, let's consider this small route planning problem here. We want to get to London from different source locations, source positions, Madrid, Paris, Istanbul, and the distance of getting to London, or cost of getting to London, is the Manhattan distance from wherever you are to London. And the simplest thing we often do in planning is to assume unit costs. Of course, it's extremely inaccurate if you say flying from Madrid to London costs as much as flying from Paris to London, but that's one possibility. Slightly more accurate representation of costs are just using constant costs. We take the Manhattan distance of 14 from Madrid, the Manhattan distance of 5 for Paris, and so on. That's fine, that's at least better than unit costs, but it's still somehow unsatisfactory, because the fact that these numbers here, the 14, 5, 10, and so on, are actually Manhattan distances in a certain grid graph is completely lost. We don't see it from these numbers anymore. That is flattened out numbers on Manhattan distances. So what we would sometimes like to have are state-dependent action costs, where we sometimes simply write down the cost of flying to London from some arbitrary initial location is the Manhattan distance from there to, and assuming that London is the center of our coordinate system, that's simply current x plus current y, absolute values. And intuitively, this is state-dependent, and it's also state-dependent in a formal sense, because these state variables here are now part of the cost function. Okay, so that's the motivation. The question is, why should we even study these state-dependent action costs? Okay, as I just said, from a human modeler perspective, they're quite natural, maybe also elegant, and we also hope that if a human modeler can rely on these state-dependent action costs when modeling, might introduce fewer errors in the domain model. There's less to write, there aren't these weird constant numbers, just Manhattan distance, for example. But it's also helpful for machines, for algorithms dealing with planning tasks. This higher structure in the planning, the cost functions, might be possible, we might be able to exploit them in algorithms, and not only is it more structured, is this representation more structured, it's also smaller in many cases. You have fewer redundancies. For example, you have to write down this fly action only once, preconditions only once, effects only once, and just one cost function, as opposed to n copies of this action for the different locations where you start. And in the best case, this can be exponentially more compact than such a flattened out representation in the number of state variables the action cost functions depend on. Now, if people haven't looked that much into state-dependent action costs in planning, I believe that the reason is not so much missing language support, but rather missing algorithms. The language support is there. So in different PDDL variants, you can express state-dependent costs. In Riddle, you can do this. Also in MDP-based formalisms, you can do it. Okay, sometimes in MDPs, these state-dependent costs will appear in disguise as state-dependent rewards. State-dependent rewards, state-dependent costs, up to minus sign, that's the same thing, as long as you want to either maximize cumulative rewards or minimize total costs. And there are applications for which this is interesting. For example, you can model preferences using state-dependent costs. An action is less costly if more preferences are already satisfied. Similarly, you can model soft goals, and a complete domain is the power supply restoration domain that also models preferences as action costs. So you have the preference that as much power is already, power supply is already restored, and this makes your action cheaper. Okay. So that's the motivation for looking at state-dependent action costs. The question is, what is the, how can we handle them? First of all, there's some good news. If you do a forward search in the state space and arrive, say, at state S and want to know what action A costs there, this is easy to evaluate. You know the action cost function for A, you just plug state S in, and you know what it costs. So you always know your transitional cost labels in forward search, and if you sum them up, you get your G values. So computing G values in forward search is so easy. What is more complicated is reflecting these state-dependent action costs also within heuristics. Different heuristics, say abstractions, delete relaxations, aware of state-dependent action costs, because for that you need to do some look ahead. How does this look ahead deal correctly with these costs? Or maybe we don't even have to make these heuristic state-dependent action costs aware. Maybe we can just compile them away and then run classical heuristics on them. And these are the two things I want to talk about: compilations and state-dependent action costs, aware heuristics. Okay, and the way I'm going to present this, the roadmap, is this. I will start with compilations from very simple, naive compilations to more refined ones. And, when you refine these compilations, this very, very naturally leads you to a certain type of decision diagram to represent these action cost functions, namely so-called edge-valued multi-valued decision diagrams. So they're like PDDs with two differences. You don't have only two outgoing branches, 0 and 1 branch, but possibly more for finite domain variables. And the values are not the sync nodes, but they're distributed along the edges of these decision diagrams. That's what they're edge-valued. Okay. And then, once we've defined edge-valued MDDs, we can formalize and discuss these compilations I mentioned and relaxation and abstraction heuristics. Here's a running example. Household domain with 3 actions. You can vacuum the floor, you can wash the dishes, and you can do the housework. They all have trivial preconditions, so they're always applicable, and they do what you would expect them to do. So vacuuming the floor has the effect that the floor is clean, washing the dishes has the effect that the dishes are clean, and doing the housework is kind of a macro action for vacuuming the floor and washing the dishes, so the effect is both the floor and the dishes are clean. And all that's interesting about these actions is encoded in these cost functions. For example, vacuuming the floor costs, these are idols in brackets, 2 times whether the floor is dirty or not. So if the floor is not clean, this is 1 times 2, so then it costs 2. If the floor is already clean, not floor clean is false, and the entire function evaluates to 0. So if the floor is clean, there's something to do, it costs 0. If it is dirty, there is something to do, it costs 2 units in this case. Washing the dishes costs 0 if the dishes are already clean. Again, there's nothing to do. And if they're not clean, if they're dirty, it costs at least 1 plus 2 additional units if you have to do this dishwashing manually, if you don't have a dishwasher. So this cost function of washing the dishes depends on 2 state variables, dishes clean and have dishwasher. And since the do housework action is a macro action over combining vacuuming the floor and washing the dishes, its cost is the sum of the costs. Okay, now I'm going to look at 3 possible compilations, 1 to 3. First, parallel action decomposition, then purely sequential action decomposition, and then the EVMDD-based action decomposition that basically combines compilations 1 and 2. Let's start with the first one. That's the dishwashing action that depends on 2 variables, whether the dishes are clean and whether we have a dishwasher. So we have 4 combinations of them, and if the dishes are clean, it costs 0 no matter if you have a dishwasher or not. And if the dishes are dirty, it either costs 1 if you have a dishwasher or 3 if you don't have one. And now you can simply turn each of these arcs here into a new smaller action. So 1 copy of wash dishes with these fixed parameters, dishes clean and have dishwasher. We encode these have dishwasher and dishes clean in the precondition, in addition to the precondition that was there, that happened to be trivial in this case, and we keep the old effect, dishes are clean in the effect, same for all the other 3 arcs, and now we have constant costs for all these actions, 0 and 0 for those 2 here, 1 and 3 for those. Okay, well, this is simple, so what to do is to transform each action into multiple actions, 1 for each function state relevant to the cost function. You add that partial state to the precondition and use the cost of that partial state as a constant cost of your new action. Now this compilation has, well, exactly one advantage and one drawback. The advantage is it always works. You can always do it. The problem is you get an exponential blow-up. I mean, you see it here. If you had a third binary variable, you would have 8 arcs here, so it's 2 to the n for n binary variables. So this raises the question, can we somehow avoid this exponential blow-up? And the answer is, well, sometimes. And that's what the second compilation is about. Instead of multiplying out all the domains of the relevant variables of the cost function, we test these variables sequentially. This works, for example, for the wash dishes action under the assumption that we have a dishwasher, so it simply costs 2 times whether the floor is dirty, plus 1 times whether the dishes are currently dirty. And now, instead of testing these 2 state variables, floor clean and dishes clean, in parallel, we can test them in sequence. So we first test whether the floor is clean. If so, partial cost 0. If it's not clean, we have partial cost of 2. And then we take care of the dishes. If they are clean, partial cost of 0. If they are not clean, partial cost of 1. And now, well, again, in this case, we get 4 compiled actions. But if you generalize this to more than 2 state variables, you see that it's only linear instead of exponential. So you have to do housework 1 action here for testing whether the floor is clean. That costs 0 or 2. And a 2 housework 2 action for testing whether the dishes are clean or not. That costs 0 or 1. And yeah, what's interesting about this encoding is that it basically goes back from this high-level macro action to these micro actions that were already there anyway. I mean, this is the do housework action, and we automatically decompose it back into the micro actions that it consisted of anyway. So, if the costs are additively decomposable, we can view our high-level actions as macro actions and simply go back to the underlying sequential micro actions. Now here the well, benefits and drawbacks from before are kind of reversed. On the one hand, you only get a linear blow-up, but unfortunately, this compilation isn't always possible. You don't always have a cost function that is simply the sum of weighted independent state variables. Some more properties, because we now turn one action into several sequential micro actions. Of course, the plan lengths aren't preserved anymore, but at least the plan costs are. Often that's good enough for us. And well, if you don't pay attention, this blow up you got in the representation before, in this first compilation, simply turns into a blow up in the search space. So, for example, if you have these 2 things, floor clean and dishes clean, then no one really tells you yet which action to apply first in your search space, whether to take care of the floor first or of the dishes, and then instead of getting this blow up into representation, you get blow up in the search space. But this is easy to fix if you just impose a priori ordering of these variables you test. So if you say, first take care of the floor and then take care of the dishes. And last thing to pay attention to, you should try to fire all these partial effects coming from cleaning the floor and cleaning the dishes at the very end of the compilation. Otherwise, there might be some interference with other compiled actions. Okay, so now we have one compilation that always works but is exponential, and we have another compilation that doesn't always work but that is linear. Can we somehow combine those? Can we get the best of both worlds? And we make it always work, kind of. And well, that's what compilation 3 is about. Let's look at the original cost function of 2 houseworks, the more complicated one with the dishwasher. It's still 2 times whether the floor is dirty, plus whether the dishes are dirty, times 1 plus 2 whether you have a dishwasher or not. You don't have one. Now the compilation could look like this. Again, we first test for this additive, for this summand, and then independently test for the combination of whether the dishes are clean and we have a dishwasher. The 2 variables occurring in this product here. And now the question is, do we stop here or can we still somehow improve this figure? And we can improve it. So this right-hand portion looks a bit strange. So if you already kind of think of it as a decision diagram, it looks odd that you branch over 2 variables at a time and not over 1 variable at a time. And also you can see that once you know that the dishes are clean, it's really completely irrelevant whether we have a dishwasher or not. There's nothing to do anyway, so the costs are 0. We don't care whether we have a dishwasher or not. And if we exploit this observation, we get something simpler. So the left-hand side still looks as before, but the right-hand side is simpler. When the dishes are already clean, we can skip the test of whether we have a dishwasher or not, and add partial cost of 0. If they're dirty, we get a partial cost of 1 plus possibly another 2 units. If you don't have a dishwasher, or 0 if you have one. I'm not going to show you the compiled actions now. This would be 2, 4, 6. You'll see the compilation later. Okay, so general thing in this compilation is you exploit as much additive decomposability as possible, but if this is not possible, if you sometimes have to factor out variable domains, you do that. There are some technicalities. You have to fix the variable ordering to ensure that your branching factor in your search space over the compiled actions doesn't become too large, unnecessarily large, and you perform something that looks like isomorphism or Shannon reductions. For example, skipping the have dishwasher here looks like a Shannon reduction. So now this is always possible again, like the first compilation. Unfortunately, still get a worst case exponential blow up, but I don't see how this could still be improved. Again, line lengths are not preserved, line costs are, and we still have to enforce an action ordering and make sure that all partial effects are fired only at the very end. Yeah, right. So this is the third compilation provides an optimal combination of these first 2 sequential and the parallel decomposition. Given we have fixed variable ordering of the variables we branch over. And the next question is, can we somehow find these compilations or these underlying graphs like this one here automatically? And now the good news is we don't have to do anything. These graphs already exist. There's a theory for them. They are called reduced ordered edge value multi-value decision diagrams. So these are decision diagrams for arithmetic functions. So if you know PDDs, those are decision diagrams for logical functions. And now here we have arithmetic functions. Like other types of decision diagrams, we have decision nodes with associated decision variables. The decision variables would be state variables for us. And we have edge weights. And these edge weights, they encode partial costs contributed by certain facts, by certain variable value pairs. Like partial cost of 2 for not having a dishwasher. And although they can be exponentially large, in many typical cases they are not. They are still reasonably compact. They satisfy all these requirements for compilation 3 I mentioned before, and they're all even almost uniquely defined by these requirements. There's one tiny technicality in these edge-valued entities. You typically require that the weight of the cheapest outgoing edge of each decision node is 0 to normalize them. I didn't introduce this requirement here, but except for that, edge-valued entities are exactly the thing you want to use if you motivate through compilation 3. They already have a well-established theory and tool support, and they detect and exhibit additive structure and cost functions. For us, this means, well, let's just exploit this. Let's represent our cost function as such edge-valued entities, exploit the additive structure exhibited by them, and use the tool support and theory. It's already there. Before I talk about edge-valued entities and these compilations and everything, one last remark. The way I motivated the entities, or derived them, was through compilations. So they're kind of graphs specifying how to decompose or compile away action costs. But it's only one of 2 possible views on them. You can also just think of them as data structures that you could use to encode action cost functions completely independently of how you use them next. So you don't necessarily have to take these graphs and base a compilation on them. you can also use them directly in the search. So later I'll talk about how, for example, you can use them to compute abstract cost values without going to a compilation, or how to plug them into the relaxed planning graph and get HL values out of that. Okay, here's an example of an EVMDD. Of course, you already saw one, but now I'm going to draw them top down and with edge weights on the edges and tested variable values on the edges. So let's say we have a cost edge-valued entity for an action cost function xy squared plus z plus 2, where x and z can take values 0 and 1 each, and y can take values 0, 1, and 2. Then we have the stack here, diagonal incoming edge that takes care of this weight of 2 here. So it's this one. Single terminal node at the bottom, and decision nodes for branching over the variables. Decision node for branching over x here, here's that here, with these associated decision variables. Edge labels, these are the domain values of the variables that get tested, and edge weights, these are the partial costs contributed by the arcs. 0 here, 1, 0, 1 here, and so on. How do you evaluate this? So assume you know you're in state S, where x is 1, y is 2, z is 0, and you want to know what is the cost of action A in state S. Then all you have to do is to follow the unique path from top to bottom, corresponding to the state here, and adding up the edge weights. So start here, 2 plus x is 1, you take this arc, get partial cost of 0, then y is 2, you take this arc, get partial cost of 4, and test z, 0, partial cost of 0, and sum of these is 6. And you can easily check that if you plug in x1, y2, z0, here you get the same value. Again, what is it? 1 times 4 plus 4 plus 2, 6. Okay, that's how edge-valued MDDs work. They're guaranteed to exist if we have only finitely many finite domain variables. They're also unique if they're reduced and ordered, and if we make sure that the minimum outgoing edge weight for each branch is 0. And even more, they support basic arithmetic operations, so we can build them bottom up. We can start with small EVMDDs and then get possibly larger EVMDD for our overall action cost function. The way this works is given an arithmetic operator, plus, minus, and so on, and 2 edge-valued entities, then we can compute an edge-valued entity that represents the sum or difference and so on of these 2 sub-EVMDDs. And the procedure you use is the supply procedure. If you have constant values, it's easy, you just add the constants, or subtract the constants, or whatever. And in the inductive case, if you have 2 large edge-valued entities, what you do is you take the common decision node, the root of the common decision node, look at the corresponding children, first push down edge weights, then recursively apply your arithmetic operator to these children, to the corresponding ones, put them together into one large, put the results together into one large entity, and pull up the edge weights from the bottom. For additive operations, this is relatively cheap, so it costs the order of the product of the entity sizes. In general, it can be exponential. Okay, now finally, we have all the background, and now I can go through these main portions. How do we compile away action costs? How can we plug these edge-valued entities into the relaxed planning graph and avoid compilation? And how can we use these edge-valued entities to compute abstract action costs? Compilation is simple now. Now that you get the idea. Let's say we have an action A with precondition P and effect F, and this cost function from before, xy squared plus z plus 2. Then to define this compilation, all we need are a couple of auxiliary variables, one semaphore variable that can only be true or false, to make sure that we don't accidentally interleave 2 compiled actions. So one compiled action, one original action can become a sequence of compiled action, and another original action can also become such a sequence. But if you want to avoid interleaving them, you can use the semaphore to make sure that only one edge-valued entity is evaluated at a time, or one original action is executed at a time, and then we need this one auxiliary variable alpha here for each action A that keeps track of where we currently stand in the evaluation of the cost function MDD for action A. Here's an example, or the example from before. You don't have to look at all the actions here, just some of them. For example, here this red one, this red arc. We go back. First of all, these auxiliary variables. They label the internal nodes of this decision diagram. One for the start here, one for this decision node, one for this, and one for the end. And in this way, they keep track of where we currently are. Okay, and now, for example, this arc here, where y is tested, where it has to have value 2, and where this action contributes partial cost of 4, becomes this action. We test whether we are here at this test point, plus 2. We test whether y has the right value, equal to 2, and we test, and we assert that afterwards we are here at this point, and the cost of this action is 4. So, and you do the same thing for all the other arcs in this decision diagram, plus we still somewhere have to take care of the precondition and effect somewhere, precondition at the beginning, effect at the end. Precondition action tests the original precondition, makes sure that the semaphore is free, makes sure that at the beginning applies the semaphore, sets alpha to 1, and at the end you do the opposite thing. If you're here at this terminal node, you can fire the effect, release the semaphore, and set alpha back to 0. And that's it. Now, if you have any type of compilation, you typically want some nice properties of these compilations. They should compile everything the way that you want to get rid of. If they don't make this sure, something is wrong. They shouldn't lead to too much of a blow-up, and the resulting output should somehow be equivalent to the original. And this is all given here. If pi is the original task with state-dependent costs, and pi prime is the result of this compilation, the resulting task is, of course, only state-independent costs. The compilation is polynomial in the size of the original task plus times the size of the largest MDD used in this compilation, and most importantly, the original task and the compiled task are equivalent, at least in the sense that they admit the same plans up to replacement of single actions in the original plan with corresponding action sequences in the compiled plan or the plan for the compilation. And optimal plan costs are also preserved. So far, so good. Now, the compilation. We could stop here, but I just want to show you that you don't necessarily have to compile away these costs and then run a classical planner on it, on the resulting task, but you can also deal with these state-dependent costs in your planner directly. And for that, I want to talk about delete relaxation heuristics and about abstraction heuristics. Let me start with delete relaxations. We know that they are informative in classical planning. Are they also, if you have state-dependent costs? Just as a brief reminder, that's the classical additive heuristic. The h-add value of a set of facts is the sum of h-add values of the individual facts in that set. And the h-add cost of making a single fact true is 0 if that fact is already true in the current state. Otherwise, it's the minimum over all achievers of that fact, or all actions that make that fact true. H-add cost of making that achiever applicable plus the cost of that achiever. And the point is here, this right thing, this cost of A, that's typically 1 or at least constant in classical planning. And the question is, how can we generalize this to state-dependent action costs, especially what to do about this one here. Before I propose something, let me give you an example. Two actions, A and B, both always applicable. A makes X true, B makes Y true. B costs 1 all the time, and A costs either 2 or 0. It costs 2 if Y is already true, and it costs, it costs 0 if Y is already true, then it's 2 minus 2, and it costs 2 as long as Y is still false. Initially, X and Y are both false, and I want to know what a reasonable h-add value of X equal to true would be. For Y, it's simple. I mean, for Y, we only have one choice. We have to apply B. This costs 1, so probably the h-add value should also be 1. The X part is more interesting because For x, we have two possibilities how to make it true. Either we can apply a right away. This makes x true, but it still costs 2 because y is still false. That's this possibility here. Or we can first apply b, make y true. This costs 1, but then the cost of applying a drops to 0, and that's better overall. That's a cheaper possibility. And well, what happened here is we know what our achiever of the desired x equal to 1 is. That's actually a. And what we are minimizing over here are all situations where that achiever is applicable. It's either applicable in the initial situation, the current situation, or it's applicable in this 0, 1 situation. And what we look for is the minimum over the actual cost of that achiever, 2 here, 0 here, plus the cost of making that achiever applicable. So bringing that situation or that context where it's applicable about in the first place. Bringing this situation about costs nothing, it's already there. Bringing this situation about costs 1. But still, the minimum over these two options is 1. So let's try to formalize this. That's easy. We just have to replace this cost of a here with cost as. And this cost as is just the minimum over all contexts in which the achiever can be applied. Cost of applying the achiever in this context plus h@ cost of bringing this context about. Tiny remark for those of you familiar with h@, you might be wondering why we have, where is it, h@ recursively in here twice, h@ of this context and h@ of the precondition of a. This only works if the precondition and, well, the variables occurring in the precondition and the variables on which the cost of a depend are disjoint, otherwise it doesn't work. But this is okay, because if a variable occurs both in the precondition of an operator and in the cost function, and assuming we're in, say, an SAS plus setting, then, well, this value it has in the precondition is fixed, and we can simply plug in this value also in the cost function. And then, well, whenever a variable occurs in the precondition, it doesn't have to appear in the cost function as well. Okay. So that's the definition. The problem is that this minimization here can become exponential. There can be exponentially many contexts, exponentially many partial states of the variables in the cost function you have to minimize over. So that's a bad thing, but there's also good news. Namely, if you run the classical, well-known additive heuristic on a compiled task, and with compiled I mean either compilation 1 or 3, that works both, then you get the same value you would get by running this generalized additive heuristic, or computing this generalized additive heuristic on the original task with state-dependent costs. Okay, but this already suggests two possibilities. Either we compile away state-dependent costs and run classical h@ on it, or we try to compute it directly. And to compute it directly, what we really have to do is to compute this cost as directly. So this minimum over all contexts where a is applicable, cost of bringing that context about plus h@ cost of a in that context. And what I want to show you next is that you can compute this cost directly by plugging the h-valued entity for the cost function as a subgraph into the relaxed planning graph. Here's the EVMD from before. Now it looks slightly different, but still this is the constant 2. This is the branch over x, over y, over z. The variable nodes, or the decision nodes become AND nodes. The weights become OR nodes. Decision nodes become OR nodes, weights become AND nodes. You add input nodes. These input nodes are basically the proposition nodes from the previous RPG layer. So they've already been reached. They have h values assigned to them, and you link them to where they're needed. So for example, where is it? Y equals to 2. It's linked to this test of y, where we assert that y has value 2. Okay. Then, to make sure that we don't forget to include h values from the previous proposition layer on some of the paths in this decision diagram, unfortunately we have to undo some channel reductions. So although the value of y was irrelevant on this branch here, we have to plug in this subgraph again because otherwise you would miss the inclusion of, for example, h add of y equals to 2 on this potential. Okay, now in the add values from the previous iteration, do the usual stuff for h add. At end nodes, take the sum of the payment costs plus the weight, and at the or nodes, we minimize. Skip a bit, and at the end, we get a value of, in this case, 9. And my claim is now that this value of 9 here is this cost value, cost AS we were looking for. And let me give you at least intuitively an idea why it is. So here we have marked in red the critical path in this edge value identity or in this RPG. So the path that is responsible for this value of 9 that you get through minimization. And now on this path, well, the variables have certain values. For example, x has value 1, y has value 2, z has value 0. And also on this path, certain input nodes are used. The one for x equal to 1 here, the one for y equal to 2 here, and the one for z equal to 0 here. And now, what I claim now is that the sum of these used h add costs from the previous layer 3, that's h add of best context, and the costs along that path 6. That's the cost of action A in this best possible context. And the sum of these two is the minimum over all contexts. Okay. So this graph here shows you almost all you have to see. Just one more remark. So this is now one action subgraph in one layer of the RPG. And you have to do this on all layers of the RPG for all actions. And one tiny thing I omitted here is that the layer isn't really overheated yet. You still have to have a subgraph for the precondition and then take the conjunction of the precondition subgraph and this cost subgraph, and then you're really done. And then, of course, you have to link everything, all the outputs to the next transition here. Yeah, so classical h-add and generalized h-add are already the same, wonderful, and this is again the same as the cost value you would compute using this RPG compilation. Okay, that's all I wanted to tell you about relaxation heuristics. Now, the last thing I want to talk about are abstraction heuristics with the obvious motivation.
Can I ask a question? So, with the daily relaxation, you know that there's a semantics where you basically each variable is a set of values associated with it. Would it help if you would be able to make your graphs work for, you know, sets or maybe for intervals or something like this? And would it, would it simplify the picture dramatically or?
Yes. Well, for abstractions, not that much. So
no, for the.
Sorry.
Okay.
Sorry for the lead relaxation, not that much. For abstractions, actually,
okay.
So actually. Now I can skip the next 20 slides.
Okay, I'll
the whole idea.
Sure,
exactly what you said.
Okay.
But it also works for abstractions.
Yeah,
for the relaxations. You have these subsets, and then you just minimize over those arcs consistent with these subsets. Then you would get the cost of a relaxed state. This might also be useful here. But it works very well for abstractions, because if you have a Cartesian abstraction, you also have subsets of domain values that are consistent with the abstract state, and then you can do exactly this minimization as part inside the scheme. Yeah. No one person will be bored by the next 20 slides.
No, I don't think
so why would we consider abstraction heuristics? Well, they're invisible as opposed to the additive heuristic, and if you want to do optimal planning, it makes sense to look into abstraction heuristics. Okay, let's look at this figure here. This is an abstract state. This is an abstract state. There are two concrete states here, two concrete states here, and action A is applicable in both of them. but it costs different amounts. It costs 1 here, it costs 2 here. The first question is, what should it cost in the abstract state? And my claim is that we should minimize here. Otherwise, we can't ensure admissibility if we maximize it to something else. So the abstract action cost should be 1 in this case, and generally there should be the action costs of action A in an abstract state as apps should be the minimum action costs of A in any concrete state as abstracted to as apps. Again, the problem is similar as before. We have an exponential number of concrete states to minimize over here in the worst case. And the question is, can you still somehow do this computation of the abstract action costs efficiently, given the size of the cost attribute entity for the concrete action cost function? And, well, I say that, well, this is possible if the abstraction we are facing is Cartesian or Coarser. It does not necessarily work if it's not Cartesian, and then we might get well, either an exponential amount of work to do or wrong results. But if the abstraction is Cartesian or Coarser, it works. And, well, Cartesian or Coarser, well, this includes many types of abstractions. It includes domain abstractions, and of course also projections. So this works for many types of abstractions. Just as a reminder, when is an abstraction Cartesian? A set of states is Cartesian if it can be written down in this form as Cartesian product of domain subsets of all the variables. P1 is a subset of the domain of the first variable, P2 is a subset of the domain of the second variable, and so on. And an abstraction is called Cartesian if all the abstract states in the abstraction are Cartesian sets in this sense. And the intuition behind this is that the variables are abstracted independently. So, in one abstract state, say, these 5 domain values are known for that variable, these 3 domain variables are known for that variable, and so on. And what we want to do, we want to try to exploit this independence between the variables and computing abstract action costs. Here's an example. This is a Cartesian abstraction over 2 variables. So variable x, which can take values 0, 1, or 2, variable y, which can take values 0, 1, and 2, and 4 abstract states. And we always have these kind of rectangles. That's why it's Cartesian. This is 0, 1 times 0, 1. This is 0, 1 times 2, 2 times 0, and 2 times 0, 1. And here is a cost function, same, not different than before. This is cost function x plus y plus 1, and an actual identity for it. First test for x, 0, 1, 2, then for y, 0, 1, 2. And the edges consistent with this abstract state are already labeled right here. Because x has to be 2, so that's only the x equal 2 are highlighted in red, and y can be either 1 or 2, so we highlight the edges 1 and 2 in red. And now we want to get the cost of x plus y plus 1 in this abstract state. So first of all, what would we expect? Cost here is 4, so it's 2 plus 1 plus 1, that's 4, and for this concrete state, it's 2 plus 2 plus 1, that's 5. And the minimum of 4 and 5 is 4. So on the way of deriving from this edge value entity, this cost of 4 somehow, without doing too much work. And what we can do is, we can simply do a top sort traversals through this edge value entity and locally minimize at all these decision nodes incoming. Here, there's only one possibility. We have this diagonal incoming edge with weight 1, so the minimum is 1. Then we can go here to this decision node, and again, look for the cheapest way of arriving at it. Again, there's only one possibility. We can come from here with an additional cost of 2. So 2 plus 1 is 3, and that's also the minimum here. And at this point down here, now we have 2 choices. We have to come from this decision node, but along 2 different edges. This one and this one. So we always get cost of 3 from here, but either plus 1 or plus 2. Plus 1 is cheaper. So that's the minimum we get. And this works. So this way you can always evaluate Cartesian abstract states directly. So you always get the abstract cost value of any Cartesian abstract state by just looking at these enabled or markdowns. Well, that's just the same story again in written. So all decision modes associated with any variable x. All those nodes, some outgoing edges are enabled, others are disabled. And the important thing is that whether an edge is disabled or enabled is independent of whether outgoing edges of any other decision nodes labeled with other decision variables are enabled or not. And this independence allows us to minimize over linearly many edges at all these decision points, linearly many incoming edges locally, instead of globally minimizing over all enabled paths in the decision diagram, because there can still be exponentially many paths to minimize over, but only linearly many edges to minimize over. And this leads to polynomial evaluation, shown with entity size. Yeah, okay, still have some time, right? Only need 30 minutes. Okay. So, one example for what happens if the abstraction you're facing is not Cartesian. In this case, two variables can be independent in the cost function, and the edge-valued entity becomes small. So like this x plus y plus 1, x and y are independent in the cost function. We can independently test them, so we get a small decision diagram, but we can make the two variables dependent in the abstraction, and then wrong things happen. Because then we can't consider these independent parts, one for x and one for y, separately anymore when evaluating this edge-valued entity. Here's an example, same cost function as before, same variables as before, but different abstraction. Something that is clearly not Cartesian anymore, it's not a rectangle. It's a diagonal plus its complement. This diagonal here, that's the abstract state representing x equals y, 0, 0, 1, 1, 2, 2. And the rest, this red one, is inequality. X is different from y. And now, suddenly, every arc here is consistent with x being different from y. So, if x is 0, there's a concrete state where x is 0 and x is different from y. Same for x equal to 1, 2, y equal to 0, 1, and 2. Now, if you locally minimize, you follow this path, 1 plus 0 plus 0. That's 1, but that's too little. Because this is like, well, assuming that the best combination of cheapest x and cheapest y, which would be 0 and 0, 0, 0, would be in this abstract state, which it isn't. And therefore, we can't use it in this minimization. So if we locally minimize here, we get local minimum 1, although the true abstract cost of this red abstract state would be 2 for one of these two colors, this one or this one. So, very last thing I want to talk about, let's say we agree that Cartesian abstractions are what we want, at least for our experiments. Cartesian abstractions somehow make sense for us. Then we still need some principled way of finding them. And a canonical way of doing this is to use counterexample guided abstraction reform. You start with a very coarse initial abstraction of your planning task, search for a plan there. If there's no plan, then you know there also can't be a plan in the original task. So abstraction is an over-approximation, and this means if there's a plan in the concrete task, then there also must be one in the abstract task. So conversely, if there's none in the abstract task, there also can't be one in the original one. Otherwise, if there is an abstract plan, we have to continue. We have to analyze and check whether it also works as a concrete plan. If it does, let's remember this here, no flaws, then we have found a plan and can use it as a concrete one. Otherwise, if there are some flaws, or at least one flaw, and this abstract plan doesn't work as a concrete plan, we have to accordingly refine the abstraction and go back to this point and search again for an abstract plan in this refined abstraction. And now let me briefly talk about these flaws here. In classical planning, there are 3 types of flaws. First of all, it might happen that if you trace your abstract plan, the concrete state you run into doesn't fit the abstract state you were expecting. This can happen because concrete and abstract traces diverge, because abstract traces or abstract transition systems can become non-deterministic. Second thing that can go wrong is that the action you want to apply from your abstract plan simply isn't applicable in the concrete state you see. Or, same thing for goal conditions instead of action preconditions. It may be that your abstract plan is completed, or the trace of your abstract plan in your concrete transition system is completed, but the goal condition isn't satisfied. And in all these cases, you have to somehow refine your abstraction. Now, in our setting with state-dependent costs, unfortunately, there's a fourth possible flaw that can occur, which we call cost mismatch flaw. It can happen that an action that is part of your abstract plan costs a certain amount in the abstract state, but is more costly in the concrete state in which you would want to apply it. And this is also a flaw you need to fix by additional refinement. Let me give you an example for this. Again, two actions, A and B, both always applicable. A makes x and y true, B makes x false and y true. B costs 1 and A costs 2x plus 1. And initially x is 1 and y is 0, and we want both to be true. So initially, the concrete initial state is this one. It's lumped together with 0, 0 in the abstract initial state. And this is the concrete goal, the concrete and abstract goal state. So what happens here? The interesting thing is this arc here, horizontal one, for A at cost 1. Action A costs 2x plus 1. The cheapest x we may assume here is 0. So it's 2 times 0 plus 1, it's 1 in the abstract state. In the true concrete initial state, 1, 0, x is still 1, and we would have a concrete cost of 3 here. Okay? But still, in the abstract transmission system, it costs 1, and so just this one-step action from year to year is an optimal abstract plan, and abstract cost 1. Unfortunately, on one hand, it's also a concrete plan. A is applicable here, but it's more costly. It costs 3 in the concrete state. And now, what do we do about this? We could, of course, use these abstract costs as an abstraction heuristic value, but then we would unnecessarily underestimate the distances. We could also use this concrete cost of 3 as an abstraction heuristic value, but this wouldn't be admissible anymore, because actually there is also a concrete plan that is cheaper than this. Namely, this one, first do B, then do A. That costs 2, that's less. So taking this concrete cost of the optimal abstract plan would not be admissible. Because of this here. Okay, so before I hand over to Flo, let me already summarize the theoretical part. We saw that EVMDDs are a compact representation of cost functions and exhibit additive structure in these cost functions. And also, what about these motivating challenges? What about compiling state-dependent action costs away? We can do that with this EVMDD-based compilation. And something that I didn't fully say for other slides, this compilation, well, it preserves the additive heuristic, it also preserves abstraction heuristics, provided that these extra auxiliary variables you need in the compilation are abstracted away. Preserved with full precision in the abstraction. And we wanted state-dependent action cost-aware heuristic values. This is possible. We saw that it's possible for the additive heuristic. We saw that we could also compute this by just embedding the EVMDDs into a relaxed planning graph, and saw Cartesian abstraction heuristics for state-dependent costs. We could also look at other degeneralization heuristics, of course. For example, we didn't look at HFF yet. One thing that really bothers us are variable orderings for edge-valued entities. We have some very naive ideas how to do it statically, but the tools we use neither support static nor dynamic variable orderings. So we just have to use the variable orderings we come up with and hope that the edge-valued entities don't grow too large. Okay, and now it's closed.
Do you want to take some questions?
Oh, yes, of course, questions first.
Could you explain why we need the semaphore variables, the auxiliary variable again?
I don't have the example with me, but if you didn't, I mean, I can give you the idea, but I can't write an example on the blackboard and show that something goes wrong if you don't have it. But, so if you have two actions, one is decomposed into 4 new, then you sort of zip them like that. Then right, and then one is finished before the other is finished. Then the effects of that first action fire change state variables. These change values of the state variables might then affect branchings later.
Okay, so
to explain it. You can easily come up with a complex example where you can draw costs. Okay. Yeah.
Seems to be in the rush that don't want to, talk about irrelevant stuff. But so I was trying to remember when you were presenting the first compilations in Mattmüller. The compilations for just conditional effects. So the first one would be kind of a direct parallel. What about the second one? Is it, the second compilation for steady Cannon effect in Bernard's paper? I can't remember. The problem is that I can't remember it. So I was wondering whether, that's the one that increases plan lengths, but potentially, but leaves the domain, doesn't blow up exponentially the domain. Does this ring a bell? Anyway, I was just wondering whether the second compilation presented, not the last one, was a parallel to this. Okay, alright.
But
probably not, but I was curious.
So, hi everyone. I talk about the practice part, and this part is split into two sections. First, I show you some libraries for decision diagrams which you can use if you want to get started with this topic. And the second section is about a compiler tool that we've written, which basically just does this word compilation Robert has shown you. So basically, you take a PDDL file with state dependent action costs, one more tool, and then you get a PDDL file only with constant action costs. So, first libraries. The first library I want to talk about is called Mattmüller, which stands for Multi-Terminal and Edge-Valued Decision Diagram Library. It's written by Junaid Babar and Andrew Minor in C++. It's open source. And actually, it's not only for EVMDDs, but also for a bunch of other types of decision diagrams. So maybe we have some need for that. But we are only interested in edge-valued multivariate decision diagrams. And another advantage of Mattmüller is that it's very nature efficient. I think the development started more than 5 years ago, and it's really fast. So even for huge decision diagrams with over 1,000 nodes, yeah, it works. I think not even a second for 1,000 nodes. I'm not too sure, but it's really fast. And one disadvantage is the documentation. So if you just get started with this topic, it's a little hard to get into because actually you have to look at the source code, what kind of methods you have, what kind of operations you can perform. So you have to look at the tests they perform and get into it. So the code is here. And actually Mattmüller is also the library we have used for all of our experiments, for all the scientific research in the past 2 years. And for that it works really well. And on the other hand, the second library I want to show you is called EVMDD. It's a Python library. It's written by us in Python. And it's also open source. But it's only restricted to edge-valued, so to EVMDDs, because that's the only thing we need. And it's also not major nor optimized. It's only, I think, a few months old. So it's nice if you just have small decision diagrams, so your cost functions are really simple. Then you can immediately run the library. But for even for medium-sized decision diagrams, it sometimes may take a couple of minutes to compute them. And the purpose for this is basically that this is our playground to play around with, to generate a decision diagram for a cost function, or to play around with the variable ordering to see how this affects this type of cost function. And the code is here, and it's also documented. And let me just quickly show you. So here, this is the documentation website, and you can see here, it's basically, I think it should have a description for everything. And here's the JIT repo. And if you would now clone this, you would have this file. It's good enough readable? Okay. So basically, all you have to do is to run this EVMDD script. And you see now we have no arguments given, so it tells you what it needs. It needs a function term in Python syntax. And then optionally you can choose the ordering and also the domain sizes. So usually we have binary domains, but maybe you have ternary domains or some other domain size. And then you can just say what it should be. So now let's just run this. I think let's use the function Robert uses most of the time, which is I think this. So it was x times y to the power of 2 plus z plus 2. And now we can run this. And actually what it does, it generates a dot file for your decision diagram. And shows you the decision diagram for this cost function. And you look, you see it looks almost exactly the same as on our slides, but for y we have actually a ternary domain. So now I give you the ordering and domain sizes, and you see actually this is basically the same decision diagram on our slides. And as I've said, for small cost functions it works really well. So if you want to get started with this topic, just load the library, choose some cost function, run the script, look at the output, and it's also really nice to get some sense, to get some feel of how the ordering affects the size of these decision diagrams. So, for example, for this cost function, which is pretty simple, if we now just first have z before y, you see that now we have two decision nodes for z instead of only one, and this can get much worse. So let me take another cost function. Okay, so basically this cost function we just have 2 times a times b plus 4 times c times. Okay, 4 times c times d plus 6 times e times f. Basically we have these 3 components with a multiplication each, and you can now see in this decision diagram we have one decision node for each value, which makes sense. But actually we now change the ordering. So right now we are lexicographically ordering, and now we choose one value of each component. So this was E and F. You see the size quickly increases. So actually now we have 3, 7, 10, 40 nodes. And this gets much worse if your cost function is more complex, or even just if your domain size is more than binary. So, this was the Python library. And the takeaway from that is that if you want to get started with this, you can just use the Python library, get some feel for it. But if you want to do serious work, you want fast, or you want some power behind the computation, just choose Mattmüller. So this was it for the libraries. Now I come to the second part, the compilation tool. And before I get started, just let me quickly say that this is really recent work. I think our tool is only a few weeks old. And so it's not completely bug-free, it's still in a very early version, and if you have some comments, if you think something we do is wrong, it should be another way, or you have suggestions, just tell us some feedback, so we can implement that. So usually in PDDL we have this increased total cost effect, which basically for most of the domains, or for the constant cost domains, is just a number, which is the action cost. And then we have in our problem file the metric minimize the total cost. And for our tool right now, for the action syntax, basically besides these parameters, precondition and effect of the actions, our tool also needs a cost field, which basically just says, it just describes the cost function of the action. And we are probably also, just allow to put the cost function in the increased total cost expression, but right now the PDDL files with state-dependent action costs need this additional cost field. And what we will do now is that I will show you some classic domain we will modify this domain a little bit, add some state-dependent action costs for action, then I'll run our compilation tool, and then use fast download to generate a plan, and you'll get a plan. So this hopefully works all well. Let's first talk about the domain. Initially we used the clipboard domain. I think hopefully everyone knows it here. Basically you have a robot with 2 arms, you have 2 rooms, and a number of balls, and the robot can either pick up a ball in 1 arm, it can drop a ball, and it can move around between the rooms. And the goal is of course to get all the balls from one room in the other room. And what we do now is we modify this a little bit so that it's the color clipboard problem. Okay, colors are fine. And this is still very much the same problem, but now we have a red room and a blue room, and we have balls with red color and balls with blue color. And the app now, or what we do now, is we make the move action state dependent, and what we just say is that the cost of the move action depends on the balls, on the number of balls that are in a room with another color than the ball color. So for example, in the initial state, we have 2 blue balls in the red room. So if we now immediately move from one room to the other, the move action will cost 2. But if we would now be in a state where the red balls are in the red room and the blue balls are in the blue room, the move action actually costs 0. And important is the goal did not change, so we still want to get all the balls from the red room into the blue room. And let me just show you the cost function. So this is one way we can write this function. Basically we sum over the rooms and the balls, and then we have this check here. If the ball is at the room, and if the ball is red, and if the room is blue, then our cost increases by 1, because this actually then evaluates to 1 to 2, and this is 1. And we have the same check, but just if the ball is blue and the room is red. So what I will do now is, actually Christian Moos was so nice to put our tool in this editor of planning domains. So if you don't know, this was the tutorial before us, editor of planning domains, planning.domains, and where you can run a solver and you can also run plugins. And Christian actually put our compiler as a plugin. But I have to say, if you now use this URL, you won't immediately get our tool. Later on I will maybe shortly explain why that is. But what we do now is we take the clipper domain. Okay. And what we do now is we make it transform to the color clipper problem. This is really easy. Also, actually, we just have to label the colors. So this is everything we need. We have red balls, blue balls, and red, blue, red, and blue. And now we just add the action costs. And to make it simple, I just say that the pick and the drop actions cost 0. So you can pick up a ball or drop a ball, it doesn't cost anything. And now we write the action cost for the move action. And let's just look at the slide again. So first we sum over the rooms and the balls. For this we also have the sum, which takes a parameter list. So sum over the ball. And then for the condition we have a huge conjunction of the parts. Opposite, the ball is in the room. Then if the ball is red, and if the room is blue. Okay, so this is the first part, this upper part. Then now we have, of course, another part. And of course everything is prefixed in PDDL. So this. Copy this and change the colors. Red. Okay. So I hope this works. So what we have now this PDDL file is statement action cost. We just have to get the colors in the problem. So room A is the red room, room B is the blue room. Then we just say that point 4 and point 3 is red. And point 1 and point 2 are blue. And this is actually everything we need. So now we can just press this button here, convert our domains. And actually this is the online editor has a 15-second timeout, so for more complex cost functions, it may be that you get an error message because it takes too long. But what we have now is we have this compiled PDDL files here, and what this actually does is that it just calls our tool, which can be found under this URL, which I'll show you later again. And on this side we also have an example file. For the PDDL file, we have the BNF grammar, which most of the time, or most things are just things you already have in PDDL3. And we also have a direct link to this online compiler. And what this now does is it calls our tool and channels this compilation. So just as a reminder, we have these semaphore variables, we have these auxiliary variables, and then for each edge in the decision diagram, we have an action. For example, here, as Robert told you, we have to check if y is 2, and we have to check if the auxiliary variable is set, and then we have this cost of 4. And what you actually can't do in the online tool currently is to show the EVMDD, but with our tool you can do that. So nice. So this is actually what it's called. This is a little hacked currently into the translator part of fast downward, so you don't need fast downward, but it just uses the translator part. Hopefully you will get this a little more decoupled in the next version. And you can see down here, these are the action cost formulas, main actions. And you see also that it gets instantiated, so we have actually 4 balls. For both parts of the action, and also the actions get instantiated. And what you can now do is you can let you visualize the decision diagram for the actions. And this is the decision diagram, which is the baseline of which is used to generate the compilation. So hopefully in our online tool we should also have first a decomposed action part, which first checks the precondition of the action, and then the next action should check this variable if the ball 1 is at room A. So let's look at the output. So this is the domain file. You see here we have some, we have these auxiliary variables which are actually not so few. And now here we have the first action decomposition, which is basically the action to move between room A and room B. Then this is the precondition part, so we check the precondition if Bobby is at room A, and we also check if the semaphore is not set. And as our effect, we add the auxiliary variable. So basically, in our decision diagram, we are now at the first decision node. We had a weight of 0 at this edge. And now you see here the first 2 actions, or the next 2 actions, are actually the condition checks for the variable if ball 1 is at room A, if it is false or true. And all of these actions are actually cost 0, because if we look at this diagram, most of the edges are at weight 0. But down here, so at some point we have a check for red room A, which should have some action cost. So, what? So here we have a total increased total cost of 2, and right, here is total cost of 1. And what we can now do is we call fast downward with these problems. And hope that it generates a blend. Right, it's found. Now let's look at the blend output. What does it do? Well, first it picks up ball 1 and ball 2, so it first picks up the blue balls, then it moves between the rooms, and this is actually the move composition with its the action decomposition. So we have all these checks, all these sub-actions, let's say. What does it do? It tops all blue balls. Here. Then it moves back again. It picks up ball 3 and ball 4. So it picks up the red balls and it moves between the rooms again and drop the ball. So first we pick up the 2 blue balls, we move to the blue ball, drop the 2 blue balls, move back, pick up the red balls and bring them to the blue room. And unfortunately right now we can't see the blank cost, but we can look at the output plus downward generates to see how much the blank costs. So let me just quickly ask you who thinks the cost has a plan has a total cost of 4? Who thinks the plan has a total cost of 2? Who thinks the plan has a total cost of 0? Who thinks? Okay, so it's not so hard, but we need a planner for this problem, so apparently it's hard. And if we now go down here to the output, we have a plan cost of 0. And actually this may be a little surprising because what we do, we pick up the 2 blue balls, and actually according to our domain definition, these balls are not in the red room anymore, so our move action does not, the cost of our move action does not increase. So we move now, and basically we don't have any ball with another colors in the, all the balls have the same color as the room they are in. So this is a little boring. That's why we load a little harder problem here. And this is the same domain, but now we have 6 balls, and ball 6, 5, and 4 is red, ball 3, 2, and 1 is blue. Now we compile it again. So actually now our cost function is a little more complex, so we have a larger action decomposition. Call it planner again. And it's found. So what does it do? Well, it picks up first 2 blue balls, it moves between the rooms, and you see now here we have much more sub-actions because our cost function is more complex. It drops only 1 blue ball, okay, then it moves back. It picks up the remaining blue ball, so ball 1, ball 2, and ball 3 were the blue balls. It moves back in the blue room, it drops the 2 blue balls, so now we are at a state where we have the red balls in the red room and the blue balls in the blue room. And what it does is it moves back, picks up 2 red balls, moves back into the blue room again. It drops only 1 red ball. Okay, this makes sense because actually if we drop both red balls, our move action would then cost 2, but now it only costs 1. It moves back again, picks up the remaining red ball, and drops both of the red balls. And let's now look at the output. We have a total cost of 4. So, and actually, you can now see here a little better. First we pick up the 2 red balls, the 2 blue balls, sorry. We move between the rooms, and you can basically see which edges in the decision diagram are checked. And we have here this check that ball 3 is a 2A, this is 2, ball 3 is a blue ball, is 2, and ball 3 is and 2A is a red room. So now with these, so now this edge has a cost of 1, and basically if we sum this up, this just means that our in this state our action to move costs now 1. And you can see that if we here's the point where we have dropped all the blue balls in the room. So now the action only costs 0 action. And if we drop a red ball later on again, which is down here. Yeah, so here we drop a red ball in the blue room, and now the action once again costs 1 instead of 0. And yeah, so that's it basically for our tool. Here's the URL if you want to check it out. As I said, it's not completely functional right now. It has still some bugs, and we are currently rewriting most of the source code. It uses our library. That's also a reason that it may get a little bit slow to compile if you have complex cost functions. It's in Python, it's open source, and if you have any suggestions or complaints or something else, just tell us so. And yeah, I think that's everything for the practice part. And before questions, I want to give some acknowledgements. First, thank you to Christian Moose, because he took the time to get our compiler running in the cloud, so that you can just use the online editor to edit your PDDL file. Then one acknowledgement to Eric Bacher, a student of us, who started this whole compiler project as a master project, and initially did most of the work. And then, of course, one acknowledgement to Thomas Keller, who did most of the research behind this whole static action cost stuff with us for the past 2 years. And unfortunately, he's not at ICAPS. He would love to be here, but he has a good reason to be here. And not only one good reason, but 2 good reasons. He's the father of twins, 2 girls, since Thursday, I think, or Friday, something like that. So that's the reason he can't be here. Congratulations, Thomas. And yeah. So parents and so on for them online. So if you have any questions, just ask them. Okay. So one thing I want to say is, because I have 2 more minutes, if you just for this editor blending domains, Christian has done much more work, and you have these plugins. And actually, you can now here install our compiler. But so the compiler should work, I think. But actually, if you try to solve it, it does not use fast downward, but uses I don't know, the planner of Mir and Christian and so on. And this planner can't handle action costs. So this would not work if you would try it that way, because that's the reason you have to use the URL which is under the compiler, and just this link basically it adds our plugin immediately and uses fast download and as a solver behind it. And yeah,
I have a question. I got a bit confused in the end. So when I compile the problem using the EVMDD, do I then still have to use the EVMDD in the relaxed planning work when I compute the relaxation heuristic, or is this then
No. Then you so basically either you compile it or you plug in your EVMDD into the relaxed planning part. But for that you have to work on your source code. You have to change your search. You have to put in your EVMDD things into your relaxation code, and so basically you can also just compile it and use this then, which most of the time probably also works.
I'm sure you're not unhappy to go to lunch 15 minutes after. So, yeah, thanks for being here.